So, shall we start? Hi, everybody. Everybody's doing fine? Yeah. So, today we're going to talk about attention. It's a very interesting topic. So, we ended up talking about encoding, decoding last time, right? You remember that? So, what was the idea of encoding, decoding? So, we had this particular example. We had this cat, and we wanted to just write a sentence about the cat, right? So we wanted to have a model, one neural network, which we can give an image into it, the image of the cat, and then this guy starts to talk about this cat, right? So we do know how we can make a neural network to talk. I mean, just simply do a simple language model, right? So you get your RNN, and then you start just fitting whatever you want, I mean the bunch of sentences to it, and you keep training it, and then when you train it properly on enough samples, then it starts to just talk, right? So if you give a random start to it, it's going to just start with a random sentence, right? First word, and then the first word goes back to the neural network. It's going to give you the next word, and so on, so you're going to have the complete sentence. This is the way that we made the RNN, and we said if we wanted to make it to talk about the cat, how we could feed the cat into this neural network? Through the initial hidden state, right? You remember that, right? So this was the idea of encoding, decoding. So the encoding is happening by this convolutional neural network here. So we get the image of the cat. The image of a cat is passed through the convolutional neural network. It's going to be processed and processed and processed till you get to the very last convolutional layer, right? And then at that part, when you flatten everything, you don't need to do anything further. So you cut the remaining of the network. You get that feature vector, and now you give it as the hidden state to your RNN, right? So this hidden state is telling your RNN that you should talk about something with these features, and that thing is essentially a cat, right? So it's going to start talking about the cat as long as you train it exactly the same way that you train the language model, right? So this is a very general idea, the idea of encoding and decoding, and it's pretty much whatever we nowadays do. Like any architecture you can think of, in some sense, it consists of an encoder and a decoder. Anything. Like transformer, again, it has an encoder and decoder. Autoencoders are encoder and decoder architecture. It's a very general idea. So the general idea of encoding, decoding is that you start with any type of sequence that you have. This could be essentially a complete sequence. It could be one single sample, right? Like an image. So you get your input sequence and you pass it through one architecture. That architecture depends on the type of data you are giving to it, right? So here is an image. The best thing you can think of is a CNN, right? But if you have a sequence again, what do you do? What do you do if you have a sequence and you want to encode it? Again, an RNN, right? So you're going to start with one architecture which is fit to what you want to encode, and then you pass your input through that architecture. You're going to get a bunch of features at the output. Then you're going to feed that feature to another architecture, which is going to give you back the type of sequence you want, the type of data you want, right? So this is the encoder part. The CNN is the encoder part, and the decoder part is the part which is taking the output of that encoder, which we call it the encoded features, right? So everything about that cat is somehow encoded into that final feature coming out of that CNN, right? So that thing is the only thing you have talking about the fact that your input was a cat, right? So that thing has encoded cat into it, right? With all the details of the image inside that, right? And that one is going inside your decoder. Now your decoder has some information about the cat, and it can start just generating something about the cat. And as long as that architecture is able to generate what you want, if you do proper training, then it should be able at the very end of the day to do that for you. So the decoder architecture now is this RNN here, which is taking the encoded features and then it's going to do what a language model does, right? So it's going to get those encoded features, then it starts with the start word, and then it just generates one word, which is supposedly the first word of a sentence that is going to be about the cat, right? Because it knows that it should talk about the cat, right? And it keeps on talking till end of sentence, right? So it's able to generate what you want. It's able to get something as input in addition to the start word, which is going to be the output of your encoder, and it's essentially decoding whatever you have encoded in the CNN, right? So this is the architecture of like encoder-decoder architecture. And as I told you, many architectures, many neural networks you use nowadays are encoder-decoder. For instance, UNet, many of you might have heard of it. When we were at the ResNet part, I just gave you as an example that still uses skip connection. It's again encoder-decoder. I mean, it's going to go down to some latent space, so just encode, just generate a bunch of features, and then essentially you're going to decode till you get into the output. Even if you want to be very, say, theoretical, very abstract, you might say that CNN itself is a kind of encoding-decoding architecture, right? You start with the image, you encode it into the features, right? And then you give those features to your MLP to decode it into the class of that image, right? But it was a very dummy, simple encoding-decoding, right? It was not this kind of decoding that you're getting from a totally different data type to another data type, right? But it was still a decoding, image to its class, right? So you pretty much can think of anything you have done up to this point as encoding, decoding. And once you think of it like this, then you can always use whatever you know to put as encoder or decoder, so you can combine any bunch of architectures together to make what you want map into another one. So now, as I told you, you can use any kind of neural network at the place of encoder and decoder. For instance, in this particular example, I just did it by CNN because I looked at the image. It's a kind of RGB image with lots of pixels. But you might say I want to do it with a ResNet because I know that ResNet is doing better encoding, feature extraction. You just replace it by a ResNet, right? And you should cut that ResNet at some point where you feel like you have enough features. Probably somewhere before you just feed it into the MLP for classification. You need to cut it there, and then you take those features and give it to your RNN, right? You can do the same thing putting one simple MLP. Maybe your image is not very complicated, right? Maybe it's just MNIST image, and you want to have a language model which looks at the MNIST image, a handwritten digit, and tells you what is written there, right? And it's going to be a very dummy, simple architecture, but you can use one MLP here, and then you can train it to just say, this is 1, this is 2, and so on, right? Everybody's clear? So you can essentially put anything here, and of course, if you don't want to have a sequence, you want to have something else, you can again replace this guy with something else, right? So if you want to get one image and transform it into another image, you can do encoding by CNN, and then again you do the decoding by CNN, right? This is what we do in autoencoders, right? So we get an image, blurred image, noisy image. We encode it by a CNN or any visual model. And then once we got enough features, then we decode it into the clean one, again with a CNN, right? A visual model, right? And this is going to be autoencoder, what we talk about next week. Okay? So now here you can put anything as I told you, and we just use RNN here because we wanted to generate a sequence. We wanted to talk about that image. Now, one thing that I tried to explain you last time, it was about the fact that why should RNN talk about this cat? And I told you because that hidden information is somehow containing that hidden state, is containing information about the cat, right? So you can make it a bit more concretely formulated. This is the way that people, like when they talk about generative models, they think of it. Like when you get into real language model community, people think of it in this way. And the way that they think of is that they always look at any neural network or any model in machine learning, they think of it as a kind of model that is just computing or somehow sampling from a conditional distribution. So it's essentially computing some sort of conditional probability. How you can say it, say for instance, if we get back to a very simple problem that we had one input, this was MNIST image for instance, and we wanted to classify it. How did we do it? We just pass it over a bunch of hidden layers, for instance, MLPs, right? And then once we get the output layer is going to compute us some y. What was y when we wanted to do classification on the image? It was a softmax, right? It was computing probability, right? So that y is essentially computing a probability. And what you can say about y, you can say that, okay, if I'm talking about a particular class k, then essentially that entry yk is giving me the probability of my image belonging to that class, right? Class K. Correct? Right? So people, when they want to start thinking about these models as something that generate, which is right now what you're doing, right? You're somehow generating sentence. You are not anymore just following a completely supervised approach as before. So once you train this model can generate completely new sentence for you, right? So if you give an image, there is no ground truth anymore that this is a cat or dog. I mean, it can write any sentence about that, right? So it's starting to generate for you, right? So it's just a beginning of generation by your neural network. And the better idea is that you always think about what comes at the output or everything here in between as a kind of representer of the conditional distribution, right? What is the chance of this image being of class cat? What is the chance of this image being of class dog, and so on, right? So you're essentially computing this guy, and you can think the same way to the RNN, right? If you think of RNN, you can again say the same thing, because what RNN is doing at every single time when you are at the particular time instant t is taking the input xt, and then it's going to take the previous hidden state, and out of these two, it's computing one output for you, right? And that output, if you think again of classification, which is the case in the sentence generation, right? Because at every single time, you're computing the chance of every token. You want to find out what is the chance of the word being is, or the word being are, or the word being cat, right? You're just computing a probability. So now the output of this model at time t is essentially computing a probability, and it's giving you the probability of every single token, every single class that you have, given the hidden state that you collected from the last time and your current input, right? But as we talked about RNN, the hidden state in the last time depends on the last input, right? And the second previous hidden state, right? That one depends on the second previous input, right? You keep on going till the beginning of time. So this HT is somehow encoding, encapsulating all the information from beginning of time to now, right? So it's going to be okay if instead of that, I write it down the probability of the class or the probability of token at this time, given all the inputs from the beginning of time till now, right? So this is a better way that you can think of RNN if you get into the domain of generative models, because there you would say this model is essentially computing a probability every time for me, given the amount of information I have received up to this point. And now, if you fit, instead of HT minus 1, if you feed the cat image into it, it's going to generate you the probability of the first token, given that you want to start the sentence because your input is now a start, and the image is a cat, right? So what is the chance of the first word in the sentence, given that image is image of a cat? Maybe something about being cute and being cat and being animal, right? So this is why it's going to generate that thing. So it's not a mad action. It's not magic. I hope that you are all seeing it right now after the whole 6 chapters we had up to this point, that this is not really magic anymore, right? It's a kind of is a piece of art doing this, very piece of engineering, but it's possible, right? So it's just generating the probability of a token given that you have information about information about the cat. So that's essentially just a big bracket. So this is more investigated when you get into the domain of generative models. But right here, I just wanted to give you this idea that, okay, every time that it's generating, it's essentially just finding the probability of every single token given what it's given or fed into, right? And those things that are fed into this model at the very beginning are the features of a cat, so it makes sense that it starts talking about a cat, right? And once it knows that it should talk about a cat, then everything is over because it can generate a coherent sentence, right? And then that coherent sentence is going to be about a cat, and this is what you want, yeah? So now, what if I want to train this model? So I think this was a question of many of you last time on Tuesday. If I want to train this model, what should I do? No? I know backpropagation. Where do I start? Where do I end? And how do I backpropagate? I start from when I want to pass forward. The cat, right? The cat image. I start from there. I pass forward CNN, right? So I'm going to give the cat into this architecture, and then I'm going to pass forward. I'm going to end up at the end of the sentence. And when I want to backpropagate, I start from the end of the time in the output sequence, and I go all the way backward to the cat, right? So everything is going to get trained all together, end to end, right? So the data set that you have, it contains a bunch of images probably, and then every single image has its own corresponding caption. For instance, you have image of a cat and then something about a cat. You can put one cat with multiple captions, all of them about that picture, right? And then you're going to just increase the number of samples you have inside your data set. And then if you want to do training, well, you first start with all of the stories we did for the language model, right? You're going to do tokenization, and once you do the tokenization, you can represent every single word inside the caption with a token. Then you don't need to think of the words. You need to think of tokens, vectors, very long vectors, and you start to just do the training, right? So you're going to start pass one image forward. This guy goes through the CNN, one convolution, second convolution, third convolution, so on until you get to the very end of the CNN, right? And then you flatten everything. This goes inside your RNN. And inside RNN, it's going to just do the recursion, right? So this comes out of the RNN at the first time, goes back inside RNN, next word comes out, right? Again, recursion, next word comes out. And you keep on doing till you end with end of sentence, right? Now the forward pass is over. Now that the forward pass is over, so we pass through RNN as well, and then once the forward pass is over, you have all the outputs, right? So Y1 to YT, and you essentially have the tokens of the caption you have inside your data set. And what you want to do, you want to make your RNN at every single time give you the right output, right? So you're going to compute the loss between the output your RNN gives at every single time with the corresponding word in the ground truth caption, right? Inside the data set. Like for instance, Y1 might give you higher probability, instead of such, the token of such, it might give you the higher probability for token of he, right? And then you're going to just compute the cross entropy between your output probability and the one hot vector of token such, right? And then you try to minimize that. And if you minimize it, then next time it's going to give you such, or the probability of such is going to be very high. You get it, right? Everybody's clear? Okay, so you're going to get this guy at the output. You're now able to compute the loss, as I told you. And to compute the loss, you're going to compare every single one to the one hot vector of the token. And now you start to backpropagate, right? So all of the suffering we had through a semester, you don't need it anymore because you already know how it backpropagates, right? You start from the very end of the time, and then you just do chain rule, right? Chain rule after chain rule after chain rule. And by doing that, you're going to get back towards the beginning of the RNN, right? And at the beginning of RNN, you are able to compute the gradient of your loss with respect to the initial state, right? Because you know chain rule, because you can backpropagate, right? So this is going to be the gradient that is at the very output of your CNN. And we again know how to backpropagate through CNN, right? It was convolution. We again move backward with convolution, right? Convolution, convolution, convolution till you get to the very beginning. And now you have all the gradients that you want. You can compute the gradient of all the weights. You can update those weights, right? And this is one gradient descent step, right? And you keep on doing it till the number of epochs you have said is over. Clear? So the gradients are computed. You can just backpropagate to the beginning of CNN, and then you just update by gradient descent. So nothing is any more complex now for you, right? Everything that is happening inside this architecture, which is relatively more complex to whatever we had before, is again, every single piece of it, you can do it, right? Or at least you have a clear idea what's happening here, right? Yeah? Questions? Great. So if you got no question, then let's go for the inference. What if now we want to do inference? It means that I did the training, so I had all of those images with captions. I did multiple epochs of training. Now I have the feeling that the weights are trained enough so they are capable of generating right sentences for an input. Now I start to just select one random image out of my test data set, and then I give it to my input, to my encoder, and the encoder going to do the encoding, and then I start to read the output sequence. So when the encoded feature goes to the RNN for the first time, I have as the input a start of the sentence, right? And the feature comes, it's going to give me one probability vector. I'm going to take the token of the largest probability, right? And I feed that guy. So for instance, such is going to be the token whose probability is highest. Then I'm going to give that such again as the input for the next time, right? So I'm going to say it was such. OK, such is now the input. Get the hidden state of the previous time also and generate the next token. And it's going to be A, so I'm going to give back A here, cute, cute here, kitty, kitty here, end of sentence, I stop, right? So this is the way that I use it if I want to infer from this model, right? Image goes in and tokens come out, and I can interpret those tokens as words, right? Everybody's clear? OK, so every single time you essentially just read your output, you can feed it in the input again next time, and then you keep on going. You can also ignore it, right? It's not the best thing you can do, but you can also ignore it, right? So if your model is very strong, if your model is trained like super good, then it should essentially generate the next word simply based on the hidden state, right? Because the hidden state here is also somehow containing the fact that you talked about such first time, right? It could, but we usually don't do it, right? We usually feed that one because our models are not that strong, yeah? And extra information never harms, right? So you can essentially do it. That is not going to be a problem. Now, so you got the idea of encoding, decoding. We have image. We give a caption for it, right? But now, next thing, one of the interesting problems that many people thought about was in this domain was the idea of translating. Yeah? And actually, machine translation, at some point of time, people used to call it AI complete problem. It means like it has all the components that you need to know in machine learning to be able to solve it, right? But I'm not sure if still people call it AI complete because we are now doing much more complicated tasks. But it was at some point of time a very challenging problem. And I don't know if you're old enough, but at some point of time, if you just give a sentence to Google Translate, then if you know the target language, then it's going to be a super funny translation, because it basically just gets translation word by word and does some dummy permutation on that, and then it's totally funny, especially if the language is not like from the same family. Right? You get a Latino language and just translate it to some Sanskrit-based language, then it's totally irrelevant, right? So now, what we want to do now, we want to just design this basic translator. And essentially, when we started to think to this problem of getting one sequence and changing to another sequence, from this Seq2Seq model point of view, encoding, decoding, we started to be able to just develop some useful translators. Okay, this was one of the first times that we had machine translation really working fine. So I want to do this task, this simple task, that I want to just get one sentence from German, and then I want to translate it into English. Okay? And I want to do it by these Seq2Seq models, because essentially I have a sequence as the input, which is the German sentence. I want to generate a sequence at the output, is the English sentence, and I want to do it by one neural network. So it's essentially a sequence-to-sequence model, right? So if I want to do that, I need to do encoding, decoding, right? What do you choose as the encoder? What kind of architecture? RNN, great, because that is a sequence, right? So I'm going to have one encoder, which is RNN. And what about the decoder? What should it be? It's again RNN, right? So you're going to just connect two RNNs next to each other, and then one of them is going to be the encoder, because it's going to take the whole German sentence and it starts to encode it. Once it got encoded, then you're going to feed it into your decoder, right? And that one is again one RNN, which is capable of generating one sentence. And then it starts to look at that hidden or encoded feature coming out of the encoder and tries to decode it into the English sentence, right? Everybody's clear? Okay, so let's do it together. So what is going to happen here is that we're going to start with some dummy initial state, maybe, some random initial state, whatever. The first German token goes in. The hidden state comes out. Then this hidden state goes next time inside your neural network. The next token goes in, next hidden state. And you keep on doing till you're over with your whole German sentence. So this last guy here is end of sentence token, right? End of sentence, the sentence is over, right? When the sentence is over, you're going to have this hidden state HT that I'm showing here down, right? And this HT, H of the last token inside the sentence, the hidden state after encoding the last token in the sentence, that is supposedly containing all the information from the beginning of the sentence up to this point, right? So this is the guy who is going inside the decoder, right? And the decoder, if this encoding has done properly, the decoder is going to give you back the right English sentence, because it contains all the information about the sentence that you are translating, right? So this guy is going to go inside the decoder. So you get your hidden state encoded. You give it as the initial hidden state of the decoder, right? So the initial hidden state, this S0, is basically the last hidden state of encoder. And then it goes in. Probably you start here with token start, right? So the sentence starts. Then you get your first word. Then you come out with one next hidden state. You decode your second word. And you keep on going till you finish with end of sentence, right? And once you finish with end of sentence, the decoding is over. Clear? Yeah?
For the second RNN, what would be the sequence of input? Like for the first union, for the first input there is.
Here, you mean?
Yeah.
This is a start, token start.
What about next?
This is what we are going to talk about. But one basic thing that you can do, whatever you infer here, for instance, you infer that the first word is I. Then you're going to give the token of I next time. You can, theoretically, you can ignore the input. You can leave it empty, right? Because still you are passing some hidden state. You're passing some information. It's not the best thing you can do, but theoretically, it's still conveying information, right? So it's still saying that the first word was I decode it, go for the next word, right? Next time you have less information as compared to the case where I put this I directly here, as you said, but still I have some information, right? It's not like I am not totally blind now, right? So you got the idea? Okay. Yeah?
I have this question that when we use the basic RNNs, not considering this, what we aim to achieve was in the inference part, we wanted to give it some input and then it starts to generate some outputs.
Yes.
But for the upper half of this, we're not actually generating anything.
Output, yeah. We are going to use it later. This is what we do in attention. But right now we are ignoring all the outputs, right? And the reason is that, I mean, if I wanted to do it right away, right? There is no guarantee that this output sentence is exactly going to happen in the same order, right? So you speak in one language and you end up with this verb of the sentence at the very end, whereas in English you give it at the beginning, right? So if you want to translate, you need to wait till the whole sentence is over, right? So you cannot really generate the output in the same time order. And this is why we are doing the complete encoding, right? So you need to listen to the whole sentence and then you're able to translate it. But you're not using the output here, right? And then I am just ignoring it right now. Later on, I'm going to use it to see where I should put my attention. This is the idea of attention. Yeah? But right now, I am not doing it. Exactly. I mean, I think next slide is showing it. So I'm just ignoring all of them, right? Questions? Everybody's clear? So, I mean, the questions your friends asked, both of them, it was quite interesting. I mean, I am ignoring all the outputs here. I'm not computing any output. You essentially can think that I just simply remove the output layer. I don't think about that, right? And here, I mean, I can take the output here, the output of the first, say, first layer, first time, and then give it back to my RNN next time as the input. This is what we typically do in practice, but at the same time, again, I can ignore all the input here. Okay, this is still theoretically correct. I mean, at the end of the day, this is not the kind of translator we want, but this is still okay if you do that. Theoretically, you are not making your architecture totally blind, right? So every time it's talking about the new word, it's just looking at the hidden state of the previous time, which essentially contains some information up to that point of time. Okay? Questions? So you got the idea how I am doing the translation now, right? Great. So if you got the idea, now let me just go ahead with the whole process, how we can just make the data set and how we can train this architecture. Okay, let's say that I have a bunch of German sentences, so I am going to make my data set like German sentences are here, and right in front of it is the English translation, right? So German sentence, English sentence, German sentence, English sentence, and so on, right? So I go for one sample, the first German sentence goes in. So the first word goes in, I ignore the output, I just look at the hidden state. The hidden state again goes back to the neural network, and I get the second token in, right? Then I get the next hidden state. And I keep on doing till the sentence is over, right? Once the sentence is over, at this point, I give the end of sentence, the last hidden state, I get the final hidden state. And the thing that I am going to do is that I need to just go to my decoding side, right? So now that hidden state goes in, and I start to just generate tokens at the output at every single time, right? And every single of those outputs is going to just specify one token, right? Essentially, it's just a probability distribution, correct? And I can look at that one, and I can look at the true English token, right? The first word in the English translation, V1, for instance, is I, right? And I'm going to compare the output probability with the token I, which is a one-hot vector, using, for instance, cross-entropy loss. And then I can compute a loss, right? I go for the next time, look at the next output of the RNN, and then again I compare that one to the second token in the English translation inside my data set. So the English sentence is going to sit here as your labels, right? Whereas your German sentence is going to sit here as your input at the encoder, correct? Right? Everybody's clear? So this is how you fit your samples inside this architecture. And if you want to do the training, essentially you do what I told you. So you start just going forward on the encoder side. You get the output, you go forward over the decoder, you finish, then you can compute the loss. No, you can backpropagate over the whole architecture, right? And the backpropagation, again, you backpropagate over your decoder, you get to the gradient with respect to the initial state of the decoder, then you backpropagate over your encoder, right? And then it's over. So that is going to be the whole training process. So you pass through your encoder part, you end up in the forward pass here, then you're going to pass still forward, you're still moving forward in time, so you are going forward till you're over with your sentence at the label sentence, the English sentence, and once you're over, you start to do the backpropagation. So you compute the whole loss. Once you computed the loss, you keep on doing backpropagation until you get to this point. This is where the whole decoding starts. So you compute the gradient with respect to the initial state of the decoder, and you move backward on the encoder till you get to the beginning of your encoder, right? Now you have all the gradients that you want. You're able to update the weights inside encoder and decoder both together, right? And you keep on doing it for every single sample you have inside your data set, right? Or it's still the mini batch. You keep on doing it for multiple epochs till you feel like the encoder and decoder weights are trained well enough that if you give a new German sentence, it's going to give you the right English translation. Questions? No question? Okay, so if you got no question, let's just have one simple example. So this, say I have this particular sample that I want to do inference now, right? So I just trained, I got a very big data set, different sentences with English translation, and now I want to do the inference, okay? And now I have this particular sentence, das gefällt mir. In German, it means I like it, and it's not just a sentence, I just put it on purpose. Because if you want to translate it word by word, it says das means it, gefällt, it means feels, mir, to me, right? So it essentially says it feels to me, right? But if you want to translate it in English, the better translation is I like it, because nobody in English says that it feels to me, right? It's the way that you speak in German, not in English, right? So now I want to just decode this guy. Now, if I have done the perfect training, what is going to happen? I'm going to start with a random initial state, H0, as the token start goes in, and it's going to get encoded, right? I get the next hidden state. That next hidden state again goes inside the RNN, and then I give the token of that word das, and this guy goes again inside RNN, you get the next hidden state. Next word goes, next hidden state. Last word goes, next hidden state, end of sentence, you have encoded, right? So now you have one hidden state which contains information about all the words inside this sentence, right? So it contains information somehow like the first word was das, the second one was gefällt, the third one was mir, and then they came in this order, right? This is the idea, correct? So this is the encoding here, and now what is going to happen when you do decoding? Well, if you want to do decoding, you are going to get this encoded version, and you give it to your decoder, and you initiate your decoder with a start. And if you are like super lucky and your model has got trained very well, then the first token coming out of your RNN is going to have the highest probability, or the first probability vector you get out of your RNN is going to have highest probability for token I, right? And then you're going to write I. Then you're going to get this I. You can essentially give it as the input next time, and you have the output of your, or the hidden state of your decoder, and you feed it back to your neural network. Then again, it computes the chance of the next word. And if you are very lucky, again, you're going to have the highest probability for like, right? So it's going to be I like, and then the last one, it, and then end of sentence, right? The decoding is finished, right? So you got your translation out. Everybody's clear what is happening? So this is going to happen when you are like super lucky. But in practice, you are not that lucky, right? If you just try it, like you get a big data set, you do it with LSTM, you're going to end up with like a nonsense translation again. Yeah. What is happening in practice? In practice, the thing that is going to happen is that you're going to get, I mean, when you want to just compute the output here, this output, as I told you, is a probability vector, right? And this probability vector, if you just do simple tokenization, is going to be of the length of all the English words you have considered inside your translator, right? I don't know, some hundreds of thousands at least, right? So it's a huge vector, right? And it's very likely that instead of I, something else gets large, right? So then, if that happens, then the error starts to propagate all over this architecture. So let's look at it once. So I told you that if you want to translate that sentence, I like it, you can also translate it word by word as it feels to me, right? Now, this means that when you are first going to decode, two guys who are going to have very high probability, very high likelihood, are I and it, right? And they are going to be different in a very, very tiny bit. Yeah? So in the order of 10 to the power minus 6, 7, right? So the chances of these guys are very close to each other. Now, what's going to happen if just you did not the best training, you did not have enough computation, your model was not advanced enough, the RNN was not containing enough weights, such that it gives you a good margin between I and it. Yeah? The thing that is going to happen, it might be that it is a tiny bit larger than I in probability, and then you start to just take it as the first token, right? Then if it goes inside your next time, what's going to happen to your RNN? It's going to say, okay, I'm going to just utter the next word, given that the first word was it, and I'm translating das gefällt mir, so I should go for gefällt, and it fills, right? So now the likely word next is going to be fills, right? It's not going to be a like anymore, because it like is not a coherent English sentence, right? And it's not going to translate that sentence, because still your RNN has the whole sentiment of the sentence inside it, right? It knows that it should translate that German sentence. But because it started with it, now it goes with the bad translation. Instead of saying like, now it's going to say feels to me, end of sentence, right? So once you do the wrong decoding first, then this is going to propagate all over your decoder towards the end, right? Everybody sees that? Yeah? So how we can prevent this? So the idea here is that if you want to prevent this one, you don't decode every single time and then you go for the next word. What you can do, you can think of the whole probability of the sentence, right? Because it might be that here it is higher probability than I, right? But then it is going to be followed by feels to me, and then you can just compute the chance of everything happening together, right? What is the chance of sentence it feels to me? What is the chance of sentence I like it, right? So you have the chance of two sentences instead of chance of every single word, right? And if you just compare those chances, probably the chance of I like it is more than the chance of it feels to me, because it's a better translation. It's a more typical English sentence as compared to it feels to me, right? So the idea here is that you don't decode word by word, but you decode the whole sentence, right? So I told you that we have two different sentences. So I have it feels to me, and then this guy has a bunch of probability, right? So the first one is happening, I mean, at the out of this guy, I am getting the probability, say, for instance, the one I showed you, I don't know, 0, 1, 2, 1, right? And then the next one, when I am computing it, it's going to be some other probability. I don't know, it's going to be 0.2 maybe. This one is 0.15, and this one is 0.11, for instance, right? So this is the case when I am translating one by one, because I here would say, okay, it has the highest, more probability than I, so I'm going to stick to this guy. I'm going to fit it back here, and then I get high probability here, high probability here, high probability here. That's the sentence output, right? But what is the chance of this whole sentence happens? Anyone tells me? What is the chance of this sentence now? It feels to me. What should I do? Say it, no worries. Multiply them, right? Why I should multiply them? I'm going to show it next slide, no worries. Just try to brainstorm with me. Why should I multiply them? Exactly, given the other one, right? This is the chance of being first word, right? This is the chance of feels being the second word, given that it is the first word. So the chance of it feels happening is this one times this one, right? Now, the chance of it feels 2 is the chance of it feels times the chance of 2 happening given it feels, right? Which is going to be this one times the product of these two, right? So the chance of the whole sentence happening is the chance of these guys happening, the product of all of these chances, right? And if I start decoding here, then I'm going to get stuck to this sentence, right? But what if this happens? Like I told you I has the chance, I don't know, 0, 1, 19, I guess I put, right? And then the next one is I like, so it's going to be 0.4, say, it. And then this is 0.9. Well, the first word here, the first word is happening with lower chance, of course. But if I look at the whole sentence, this sentence has higher chance as compared to this one, right? The whole problem happened that I start decoding at the very first word. Yes?
It seems to me the longer the sentence is, the probability will typically be lower.
Yes, but the probability of one sentence becomes lower, and this makes sense because you have more sentences than words, right? So if I'm thinking about the sentence of 2 words, say I have in my dictionary, I have 10 words, okay? The probability, if every word happens with the same probability, the probability of every single word happening is 0.1, right? 1 by 10, correct? Now, what is the probability of every sentence of length 2? I mean, it's true that not every combination is the right sentence, but let's assume that it is, okay? It's going to be, the chance of every sentence happening is 1 by 100, right? Which makes sense, right? Okay, the longer the sentence gets, the more sentences you have, so the chance of every sentence happening is getting to be smaller, right? But one sentence compared to another sentence, you still have same relative expression, right? So like one sentence, now if you think of sentences of length 2, the chances are around 0.01, right? 1 by 100. Now if one of them is 0.02, is higher than the others, right? So you're getting, in terms of the scale you're working with, you are getting smaller, so chances are now in the order of 10 to the power minus 20, minus 30, I don't know. But still relatively they are the same. Like one of them has higher chances compared to other one, right? Yeah.
But what if there is a, say in the translation kind of scenario, what if there is a wrong translation that actually have less words, and at times to get a higher right? I guess that's what you're getting at.
Yeah. But the point is that when you do the training very good, then these, I mean, I told you this is 0.1, for instance, right? But think of the number of words you have. It's order of 10 to power 6, 7, right? Right? And then the other probabilities are all around 10 to power minus 8. So other probabilities are very small. So there are just a few words, few tokens coming out, right? So you shouldn't think like you have like I, it in this order, and then something like he is also in the same. He is going to be in the order 10 to power minus 7, right? And it's not going to make any impact on this whole process. The things that are going to play any act in the decoding are those who are going to be a candidate of translation, right? But the question is which translation your machine can give you, right? Both of them. So theoretically, if you want to intuitively think about this, essentially your machine is going to give you right translation, correct translation. It's going to happen. But the question is whether it can talk like a human being, like a normal native English speaker, or it's going to just translate it word by word, right? So this is the case where it's not speaking natively. This is the case when it's speaking natively. And what is the native speech? The speech that is more probable to happen, right? So a very native English speaker could also say, it feels to me, and everybody going to understand this, right? But it's not a kind of typical thing, likely thing to happen out of mouth of one native English speaker, right? Yes, again. And your training data is again based on those native speeches, all right?
To follow up his question, are we saying we shouldn't compare the sentences that have different endings?
No, you can compare them. No, what I'm saying, I'm saying that here when I was decoding, I started to decode first token, right? And I said it's going to be it, right? So I just canceled the chance that I could also be one candidate, right? So I didn't consider what's going to happen if I put I as the first word, right? I ignored that completely. And I just went for it to be the first word. Then I am going to get stuck to the first sentence. It feels to me, right? Because once I think of it to be the first word, the most likely sentence that I can have is it feels to me. This is a right translation, right? But what if even though I was happening with less chance, what if I put I to be the first word? Then I'm going to have I like it, right? This is the next decoding possible. And now, which one is the better decoding? It feels to me or I like it? Well, I can compute the chance of both sentences and compare them, right? So if I take all of them into account, then it's going to be better translation, right? So the whole idea is that I'm not going to just decode one word and then ignore remaining, right? So I am going to think about the whole sentence at once, right? So I'm going to say, let's say that I could have this computation power, that I consider all possible combinations of length here is 3 or 4, right? If I can do that, then I would like to see what's going to be the highest probability in the sentences. I take that one as the translation. And this is going to work better than translating word by word, right? Taking the highest chance word by word. Everybody's following? Yeah.
The probability of these two sentences, are they comparable?
They should be comparable, right?
Will the total outcome of all possible translation be sum to 1? The possibility.
Yeah, but the number of sentences that you can consider, they are crazy, right? Yeah, but of course, I mean, every single token you're computing here, that vector of probability, even though it's huge, it's going to add up to 1, definitely. It's output of a softmax.
Regardless of the length of output sentence?
Doesn't matter, right? So say, I mean, think of it like that. So you start with the start here, and you give your hidden state here, and then you're going to get probability for every single token here, right? Say you have, I don't know, 10 tokens, 10 possible tokens, okay? Then if you take any of those tokens as the first word, then you're going to feed it back here, and you're going to get the next token, right? So again, you have 10 candidates here, right? And you keep on going to the end, right? Now, let's say that you just start with any possible token. At the first point, you just try all possible tokens. You see it's a tree, right? It's getting massively large, exponentially large. But you have done all of it till all the sentences you have decoded end up with end of sentence. Now you have a huge number, which I cannot even imagine how large that is. Maybe Avogadro number, something like that. Number of sentences, right? If you just add up the probability of all of those sentences, then it's going to be 1. Yes? Because it's all possible cases coming out of your decoder.
This kind of possibilities come out of the decoders depend on the overall vocabulary of this language.
Yes, I'm going to show it next slide. Yeah, it's going to be huge. You can never do it. Yeah, you can never do this. This is just theoretically best idea, but you can never do that. You're right.
But the size of data sets do affect these kind of things.
Yeah, definitely. I mean, the more data you have, the more accurate those probability going to be when you compute them, because your decoder going to learn better to speak English, right? Yeah, like anyone who learns any language, the more they speak, the better they start to talk, right? So they need to see more samples to be able to talk, right? It's the same thing happening here, right? And you can see it correctly because the number of sentences you can make in English is like unimaginable, and then you would never ever in your whole lifetime or even the lifetime of a couple of generations would get that much of sentences as input. Right? So somehow inside your brain you are doing the same thing. So you see a few samples and you start to just extrapolate it. I don't know if I made it more complicated for you or simpler, but you don't need to think complicated about this. This guy is, the whole idea is that I shouldn't just stick to one decoding. I can just candidate multiple decodings, right? And ideally, I can candidate all possible decoding. I just go towards the end, and then I look at the whole sentence, which one is the most likely one, and I take that one as the decoding. Okay?
A really quick question. What is an X and V?
X is the German sentence. V is the English translation. So what is the most likely English translation given your German sentence as the input, right? Everybody's clear? Questions?
Do encoder and decoder contain the same set of weights?
Encoder? No. They are different. I mean, this is the whole idea, right?
Right.
So
if I were to like update one of the weights for the encoder,
yeah.
all of the weights like throughout all of the time slots will be updated, but only for the encoder, not decoder.
for the encoder, yes, yeah. But of course, since the input of the decoder is going to change, the initial state of the decoder is going to change, then the outputs of decoder are going to change as well, right? But each time you update, you don't update only the encoding or decoding weights. You update them together, right? You train end to end, right? So you compute the whole gradients. I mean, the whole story here is this one. This was the idea, right? So you first start from the very end to the beginning here, and then you're going to go backward in your encoder, then you are finished with backpropagation, right? No, you update. When you are finished with backpropagation, you have your gradient with respect to the weights of the decoder and the gradient with respect to the weights of the encoder, right? So you don't need to think of that. I mean, even though for you there are two different architecture, but you don't need to think of the whole thing as two different neural networks. The very beginning, H0, X1, to the very end, when this English sentence is over, is one architecture for you. One very complicated, like multi-step architecture, right? But it's a model, right? Getting X, giving you output Y. Questions? No question? Okay, so if you got no question, let me just go ahead here. And yeah, so the idea was that I should just translate the whole sentence at once, meaning that I should just compute the chance of the whole sentence, okay? So let me see. Yeah, so this is essentially what I tried to explain when I was answering your question. So how I can do it, I can just don't stick to one, right? So I can consider all the possible combinations. So it feels to me is one combination, I don't know. It, am, or I, it's another combination, right? Because they are possible tokens in English, probably the probability of that one happening is 0, right? But I can consider that. And I can consider all possible sentences coming out of my decoder, and then I try to just take the one which has the highest probability. So how I can compute the probability is going to be exactly what we did here on the board, right? So how I can compute the probability of the English sentence, V, given the German sentence here. So given to the model, to the encoder. So essentially I start to write it down, just decouple it in this form. So this is going to be the base rule, what you did here, the probability of the first one times probability of the second one given first one times probability of the third one given the last two, and so on, right? So you can write the base rule here. Then you're going to have a chain rule here. You have the probability of every single English word given what you have given as the input from your encoder. So when the German sentence got encoded, this HT came out of the encoder. So this is the encoded version of the German sentence. These are the words in English that you have already decoded. So the first word till word L-1. And then if you know the probability of the next word given these ones, then you just multiply them next to each other, and you are going to have the chance of the whole sentence happening at the output, right? But you do know how to calculate that probability, right? Inside the product, this probability here. You know, right? How I can compute that? Any idea? What is the probability of second word in the English translation given the first word in the English translation and all German sentence? How you can compute it in your neural network? The softmax output at that time, exactly. So this is the thing that you are going to do. So essentially you are going to take your softmax of that English token, right, at the particular time, right? So you look at the output of your softmax at that time. You're going to say, what is the chance of this token happening? And then you just take it as the probability. You multiply it to whatever you have computed up to that point, right? So if you want to compute this one, it doesn't mean that it's infeasible theoretically. You can do it. So you can compute that one. And this is just a kind of indicate what do I mean by this notation. But you all already know this. So when I have this token, this means that my English word at time L is the second word, whatever that is, right? And then the probability of second word happening, given that the output of my softmax is this one, what is that probability? What is the probability of the second token happening, given that y? 0.3, right? That is going to be 0.3. So I just simply mean that you go for the corresponding item at the output of your softmax for your token. You take that one. That is a probability. You can use it. And this is conditional probability. It's not insane. It's really the conditional probability. So you're going to use it, and you can compute that one. So some of you told me that, okay, these probabilities, how they look like, I told you they are in the order of 10 to power minus maybe 4, 5, 6, 7. So they are hugely small, right? And how you can handle that issue, typically we work with the logarithm, right? So we are not going to really multiply them, because at some point your computer is going to just give you float 0, right? So you rather just work with the logarithm. The exponents is going to be much easier to work with, right? So then they are not showing that, saturation issue that you have. The only reason that you can do it, you need to do that. But at the end of the day, you want to just find this one, right? So you want to find the sentence whose likelihood to happen is very large. And now think I am just decoding all the sentences of length L. And say I have D different tokens inside my dictionary. How many possible cases I have here? I have D words So every single word in the sentence could be one of the D possible cases. And I know that my sentence is of length L. How many sentences I have? D to power L. Great, yeah, right? So if I just consider a start and end of sentence as well, D plus 2 to power L. I mean, essentially, you are not going to end up with any L, right? So not all the sentences are to be of the same length. One of them could be 4, like the one we have on the board. The other one could be of length 3, so it's going to make it even more complicated. But let's just have a rough calculation. So it's going to be in this order. So what is D? D is the number of tokens, right? The number of words in English language. And what is that? Huge, right? And what is the length of a typical sentence in English? It's typical that you talk a sentence of length 10, right? Does it make sense? Right? So you could have a sentence of length 10, and then that huge number to power 10, that is going to be huge, right? Everybody's clear? So you need to just search over this much of cases if you want to translate your sentence properly. This is impossible. You should forget about it, right? So, yeah.
Why plus 2?
Sorry?
Why plus 2?
Yeah, because I mean, at the beginning of the lecture, we just consider that we also add to artificial tokens and start of sentence, end of the sentence. But that is not really important. I mean, at the end of the day, you have a huge number to a huge power. This much of cases you should check, and then you take the most likely sentence. It's impossible, but the point is that many of those sentences are useless, right? You initially know that those sentences are not going to happen. I are potato is not an English sentence, right? It's not the right English sentence. Anyone speaking English properly would not say it, right? So you don't need to really compute the probability of this one. And so for a lot of other sentences, so it's going to end up being a search on a tree, which you can, again, using maximum likelihood search, maximum likelihood decoding algorithm, and Viterbi algorithm, maximum likelihood detection with Viterbi algorithm. You can do it efficiently, okay? So there are approaches to do that, but the most common approach that we can use in practice, so we don't need to decode everything. What we do usually in practice is that we do something called beam search. And beam search means that we are going to fix a specific number of candidates. For example, I would say, I want to have the most 5 likely ones, right? So when I first decode, so I'm not going to take only it, I'm going to take it, I, and the 3 other likely first words, right? Then I go for the next one. I would say, okay, if it's it, let's compute the next probabilities, right? If it's I, compute the next probabilities. And so on till the last one, right? Now you're going to have these 5 different cases multiplied with the number of tokens you have. This is large, but it's not huge. You can do it. And then among them, again, you're going to collect the 5 most likely ones, right? So it's going to be I like, one of the likelihoods. The other one is it feels, maybe a bunch of other sentences. And you're going to keep these 5 most likely towards the end. And then at the very end, you are going to take the highest one, the most likely one, okay? So usually we do it with beam search, and this is going to be more efficient. So we call it top K-beam search, and this is efficient. I mean, this is what we used to do before transformers come out. Everybody's clear? Questions? No question? Okay, so yeah, that's pretty much this. So this is just a technical hint, like if you want to really compute that logarithm of the likelihoods, you usually normalize it with the length of sentence as well. This is going to make it more fair comparison, but these are not that crucial in the understanding. So any questions? So everybody got the idea, right? So you feel confident you can use LSTM and make this translator, right? I mean, I know you're going to go through a very hard time, but you can do it. You understand how it works, right? Great. Any question? So I can give you a few minutes of break, but if you don't want it, I would be happy because then I can just go on with attention. Do you want it or not? I mean, 2 minutes. You want 2 minutes? Okay, 2 minutes and then we start attention. Really, 2 minutes. Okay, shall we go on? So, now, attention, guys. We're going to talk about attention. So, now, say you just try LSTM, you want to do the translation, and you're going to do it, I mean, at some point in time, in first neural machine translators, they were based on LSTM, essentially, because LSTM was the RNN, which was stable, could go through long sequences. And this was one of the first time people could just use some neural network to do coherent translation. And you do exactly what we did in the previous part, right? So you're going to get your sentence in the mother language, and then you translate it to the other language. So this is going to work fine, but this starts to somehow do mistakes when the input sentence gets longer and longer and longer. And you might guess why this is happening, right? Why this happens. The hidden state of the encoder, which is encoding, is containing the whole information about the sentence, right? But when we talked about the RNNs, we said, like, even when we do LSTM, at the end of the day, our memory is somehow limited, right? So we're not going to really touch the very beginning of time as clear as we touch the last words, right? So the LSTM, even any kind of RNN, even though we can use gating, all the approaches to improve it, at the end of the day, they have limited memory, right? And the whole issue here is happening because decoder somehow is just seeing everything through this last hidden state, the encoded version, which is somehow compactly representing your whole sentence. So this is a kind of challenging thing to do when the sentence is very large. So this is a kind of issue that we call it bottleneck. So for instance, I have given here a longer German sentence. And here in this sentence, so it says, ich habe den, this den is essentially the, okay? But you can go on, über den, this den is over which, about which, about what, right? So the second one is not article, right? But they are being translated the same, or being used the same in native language, right? Now, if you want to translate it to English, now what you're doing, your LSTM or whatever RNN is going through the whole of this sentence. So it's going to somehow take information about the first den, the second den, but it's really hard for your decoder to distinguish between these two, right? So it's very likely that when it's going to just put some word here, it just gets confused. Well, what is this den? Which of those den is it, right? Should I translate both of them as the, both of them as what, or whatever? Yeah. So it's going to be harder for your translator to do it when the sentence gets longer and longer, because it's true that the information is hidden inside that encoded version, but it's now getting harder to be distinguished over time, right? So harder to get decoded. This is what we call it the bottleneck issue. So the whole encoder and decoder are connected through one bottleneck, all right? And this bottleneck, doesn't matter how much you increase the dimensionality, at the end of the day, is just pipelining the whole information through that, right? And then this is a bit hard to be done, right? So just going from one direction, if it's cut, then everything is cut, right? So this is the issue of, information bottleneck issue, and there is one other information bottleneck issue which is very related to this one, but that is in information theory. So this is a kind of information theoretic viewpoint of the same problem, but people here and people there, probably they did not know of each other for a long time, right? But they thought about the same issue, right? From two different points of view. So if you have heard of that, this is related, but this is not that one exactly. So don't get confused with that one. So now the question is how we can resolve that issue, right? And let's just look at our example that we talked about. So here we had the German sentence, and then we encoded it. We just gave the encoder here, and then we got the decoding at the output, right? And now I told you that it might be confusing for your decoder at the very beginning whether it should put I or it, right? Because both of them are very likely to start. I mean, you can very likely start your sentence with both of them. And the main reason is because, I mean, here the sentence is not that long, but if you think of it to be long enough, somehow this hidden state is telling your decoder that there exists das, there exists gefällt, there exists mir inside this sentence, and they come with this order, but it's not telling it like right now that you want to translate which word you should start with, right? So it doesn't tell it. Now, this is the issue, but if you could tell your translator at this point when it's going to translate, pay attention to mir, right? So because we have mir in the last word, you should put I as the first word, right? So if you can give this attention to your decoder, then the decoder is going to put I first, right? And then once you put I first, then everything is over, right? Because I like it is the only possible translation then, right? The only challenge here is that at the beginning it should pay attention to that existence of this word mir, right? So this is what we call it the need for attention, and we want to just design a sort of mechanism which gives us this possibility that at every time when we want to decode, we look at the input and we see whether to which part of the sequence we should pay attention when we are translating. So you got the idea? What we want to do? Questions? Great. So, as I said, the whole idea is that once you are decoding, if you could tell your decoder, so this is when you are decoding the first word. If you are decoding your first word and you are taking the hidden state coming out of the encoder and you want to start your sentence, right? If you can tell it that you should talk about that last word, mir, don't talk about anything else. Or put more attention to that one. Be careful, like a kid who wants to answer the question. Pay attention, pay attention. If you give that attention to it, then it's going to give you I. So the chance that it returns you I is more than this case, which we used to do in the classic translator, right? Because there we are not telling the translator, the decoder, where you should put your attention, right? We just say, okay, this is the encoding, you start, right? And it doesn't know. It might start with it, right? It could happen. But the first one has the less chance to do the mistake. So this is the idea of attention. And the whole attention mechanism is trying to, again, develop a sort of computational formulation to do this, right? So let's see how exactly attention does this. So this is my encoder again, right? The same encoder as before. I started with the beginning. I start with the first word in the sentence, and then I get hidden states over and over. When I was doing the encoding in the basic form, I was just ignoring the outputs, right? I was not doing anything with the output at every time because I didn't need that, right? But maybe I can just generate some outputs, right? Maybe I can put some linear layer with some activation, some very simple one fully connected layer at the top of these hidden states. So I compute something that we call it key. So it's the key to that particular word or that particular entry inside the input sequence. Everybody's clear? So typical way that you do it, you just simply do it with one simple fully connected layer. So you get your hidden state exactly like what you use to compute your output, right? So you're going to compute some output, linear output, and then you activate it. Again, sigmoid is a very typical activation here. We don't want it to be Provolti or anything, so it can be any activation. You don't need to have softmax here, right? A simple activation is just like another hidden feature you are generating. Clear? So every single time, I am just generating a bunch of hidden features, and I call it the key. Yes? You have a question? Yeah.
In this general workflow, the yellow box references are on like
The green box, you mean? Yes.
And the red one.
The red one.
Refers to the linear layer.
A linear layer, exactly. This is a linear layer, exactly. So this linear layer contains this weight WK. Now, WK is the weight of this layer, right? And it's constant over time. It's not changing, exactly like the other layers inside RNN. So every single time that I am computing the hidden state, in addition to the hidden state, I just have one extra. So this is my RNN encoder here, which is going on as before. So now you always think in one other dimension, right? Here in this side, I am just having one hidden state. So I see one other layer, linear, fully connected layer. I see what is coming out of my hidden state at that time. I compute one key, right? And the next time I compute another key and so on till the very end, right? So that's it. I'm generating a bunch of keys. And now I am going backward and now I am decoding. Now, if I want to decode, I want to just make a mechanism where at every single point, every single step in time, before I start talking about the word, which token should comes out, just make some attention on the input, right? In the input sequence. So what I do, I first generate something like the key, which I call it query, right? So I'm going to get my first thing, like the first hidden state comes here, and then something comes out of it. So this is like the initial hidden state, which is the encoded hidden state of the encoder. Then I get my new hidden state. And now that I have my new hidden state, I don't talk immediately about the token. So I first compute something that I call it query. And what is query is, again, exactly like the key at the decoder side. So essentially, I am at the decoder side. This is the first time. So the encoded version comes in, the start token comes in, and then I get my first hidden state, right? So I get this hidden state and I compute some query. So I just pass it through one fully connected layer, for instance. This fully connected layer has its own weights, right? And then I get a bunch of outputs out of it, right? So that is my query. It's again a feature, right? Everybody clear? So I am now at the decoding part. At one particular time, whenever I see my hidden state and the new input goes in, I just compute one query, right? Now, I want to use this query to pay attention to whatever has happened in the encoding, right? How can I do it? Okay, say I am at the particular time L. Okay? I'm at this time L, so I got the input at time L, whatever that was. You just ignore it for the moment. I have my state from the previous time. Yeah, it came in, and now I generated the newest state. From this newest state, I can compute the query, right? I have the query of this time. Now I want to see which part of my input I should pay attention to, right? And if I want to do that, I can just look at the whole encoding sequence of keys, right? So when I was doing encoding, I was just computing lots of keys there, right? So what I can do, I can say, okay, I want to know at this particular time when I'm doing the decoding, to which part or to which word inside the encoder I should pay attention. So essentially, I get that query, then I just compare it to those keys. And how I can compare two vectors? Well, I can compute some sort of product of them, right? Simplest product, inner product, right? So I have one query at the output side, at the decoding side. I have a key at the encoding side. Typically, we set them to be of the same dimension, and then I compute the inner product of those two things, right? So if I compute the inner product of the query with the first key, then I'm going to get one first value here, right? One first weight. And then I do it for the second time, third time, till the last time, right? Attention to this point that I am right now, I have not yet decoded my token, right? I am still at time L, right? So I have not yet said what is the translation at this point, right? I am just doing computation. But I have access to the whole keys when I was doing the encoding, right? Because they all generated through time when I was doing the encoding. So I am able to compute my query, and then I compare my query with all of those keys, right? Everybody's clear?
When you say compare your key and query together, do you want them to be the same?
No, I'm just computing their inner product here. Inner product, it's a vector of length 10, for example, here 10, then you just multiply them entry-wise, sum them up. It represents, when your vectors are in the same direction, then it's very large. When they're orthogonal, it's 0.
So you want them to be large?
In some sense, in angular sense, right? But for the moment, you don't really need to think about that because that totally depends on the way you develop your. So you can think that there is a mathematical way that I can compare two things, right? And the way that we usually do, we just compute the inner product. And this is the angular distance, but you can do another distance. That's not important. But yes, you want them to be very close to each other in some sense. Here, you want them to just direct to the same direction, yeah.
Really quick question. When we are multiplying those two, P and query, are we just calculating the distance between those two?
Somehow, but as I said, the angular distance, right? Okay. So if they are very similar, then this query is going to be, the inner product is going to be large. If they are orthogonal, then it's going to be 0, yes?
Explain the intuition behind what we're doing again. The intuition behind us generating some keys and then doing this.
Yes, because when you are generating these keys, when you were doing the encoding, so these keys are somehow telling you sentiments of that particular point. So what is the features of the first entry in time, second entry in time, and so on, right? And then when you are computing the query, your query is of the same nature, same kind of features you are computing for your query. And then now you want to see this word when I am translating is related to which word, or I should put attention to which word at the original sentence, right? And then the way that we do it mathematically is we just compute this inner product, right? It's just a way of doing it. Maybe somebody comes with an alternative approach to compute that. That is possible. This is, in deep learning, you always just assume something, and when you do the training, it gets adapted to that definition, right? Everybody's clear? So up to this point, we have just compared our queries with all of these keys, right? And we got a bunch of weights. So these weights are potentially containing some information about how much that particular time instant at the decoder is related to every single time instant at the encoder, right? Everybody's clear? So now I can just collect all of them in form of one vector, right? And all of this vector is computed at the time L when I am doing the decoding, correct? So when I am doing the decoding at time L, when I am decoding, I am computing a vector. And that vector is of length, of the length of t, exactly, of the length of your input sequence, right? And that vector is somehow representing how much it's related to every single time instant at the encoder, right? Now, you have this vector, but now what I want to do, I want to somehow convert this vector. This is a vector of numbers, right? And these numbers potentially could be positive, negative, right? Because it's inner product, correct? But I want to make it in a form that it gives me more meaning, like better meaning in the sense that the one which is higher is giving me more attention. So how can I do that? Absolute value, anything else? Anything that we always like in deep learning? Sigmoid. But you want it to be relative, right? One of them, between all of the words, one of them should be more, I should pay more attention to that one, right? If I put lots of attention to that one, I should not pay attention to the other ones. Softmax, great. There you go, right? So I'm going to pass it through a softmax, right? If I pass it through a softmax, I'm going to get something. So I have this guy, this vector z here, this one. This is containing t different values, right? And those t different values are the t different values you computed when you checked your query with every single key, right? Now you're going to pass it through one softmax. So I'm going to pass this guy through one softmax, and then I am going to get some vector, and this vector is a vector of probability, right? One of them is large. When that one is very large, then the others are small, right? And that one that is being very large, this means that I should pay attention more to that particular time, right? Everybody's clear? So you have feeling about these guys, these alpha values? So this is what we typically call them attention weights, and they are essentially giving you the chance that one particular entry inside your input sequence, one particular entry inside your German sentence, one of the words, being related to the translation or the word that you are translating right now, right? So I want to put the first word in the sentence. I should pay attention to which one. And of course, you can never say it for sure, right? You cannot say that pay attention to the last word. But you could say, most probably you should pay attention to the last word. The chance of second word being very important is less. The chance of first word being important is very, very small, right? So you are going to put your attention based on this probability. Now, how can I use this to make my feature based on which I can do the translation? So I got this query, and I did all of that process that I told you, right? So I got the query, I did the comparison, I passed through softmax, I got one vector, and that vector is a vector of probability. And what is the length of this vector, alpha? It's t, right? Each of them is the chance of one time instead of the encoder being related to this time instead of the decoder, right? So the thing that I'm going to do, I am going to get every single of those chances. So this is alpha t. So this is the chance of time t at the encoder. And I'm going to multiply it with the hidden state of that time, right? Now, if I want to put attention to one particular time, say time 3, then alpha, the chance of that time at the encoder, is going to be 1. Anyone else is going to be 0, right? Then the value or the vector that I am computing here is going to be exactly the hidden state at that time, right? Correct? Meaning that I'm putting all of my attention to that time. Everybody's clear? So I'm not going to look at the third word through the window of the last word and putting my attention directly on the third word by putting the probability of that one, alpha for that one being 1, anybody else being 0, right? I mean, of course, I'm not doing it by hand. I mean, it's going to get trained over the training process. But at the end, if really I need to make that word being very important in the translation, then the chance alpha for that word is going to be very large. The other ones are going to be very small, right? And then at that time, when I want to do the translation, I am essentially working with the hidden state of word 5 or 3, whatever that was, right? And this is much better information as compared to the very last hidden state I had, right? Questions?
Yeah. We first need to calculate, we first need to have prediction, and then we can get the query, right?
Why we need to have the prediction?
Because based on the graph, like we first get to the yellow cell, and then we get the query.
Yeah, yes, but this is something that is coming from the previous time, right? So you did the decoding once before, right?
Yes.
Yeah, so when you do the decoding, I mean, when this comes here, you already have the next one, right? So the next one goes inside for the next time interval, right? Right now, you don't think of the time. I'm freezing the time at the decoder. I'm just at one particular instant at the decoder. Okay. Yeah? So we're just going in depth now, right? Everybody's clear? Yes?
For your reference to this weight is the weight within the integer.
This one.
And we generally like between our keys and queries, the weight to these keys and queries to adjust the AL.
Definitely, yes.
Rather than the previous.
Yes.
Previous hidden state coming from two RMs, right?
Somehow, yes. So when you do the training, I mean, gradually your encoder and decoder are going to start to understand when they want to translate this word, they need to pay attention to that particular word inside the encoder, right? So all of those weights are going to be trained in a way that you get the right attention each time.
So for the attention part, we barely adjust the hidden layer from the two RF, right? Or
For the attention part, you don't need to do any modification to your own hidden state. You just add the extra hidden layers, which are going to compute the keys and queries. And
you mean the hidden layer refers to the linear part, right? To the red box.
yes, I mean the keys are computed with that one, right? Yeah. And then you have a bunch of other things, like here the red box is computing the query, right? Yeah. Everybody's clear? Yeah.
So the step of this linear is to compare each.
To combine the information of every single time proportional to the attention weights that you have.
And then decide all of the words, which one is the
No, just we are just talking about one word. One word. I'm just decoding one word now. I'm just decoding one word here.
But why does one word need this linear part?
Because when I want to just, the first word I want to decide whether I should put I or it, right? Now I need to know where should I put my attention. Should I give more weights to the last word in the German sentence, which was proportional to I? Or should I give the attention to the first word in the German sentence, which was proportional to it, right?
So I can understand this exact word are determined by the previous entire sentence.
Yes, that is coming because you have your state here. This state is carrying all of that information after encoding for you. That is there, of course. But you're not directly using that to decode, because when you do that, you're not putting any attention. You're just looking at the whole sentence from the window of this last state, right?
So you are deciding which attention to put based on previous sentence.
Yes. Yeah. Based on what you got up to this point, right? So you want to know where you should put your attention, okay? So just please, I finish this because it's, but then I answer the question. But any question in the process here? Everybody's clear what the process is? So essentially, you compute all of those keys and queries, and then you compute those attention weights, and then you add them up, somehow linearly combine them with the hidden state at the encoder, so that you get your attention vector, right? Everybody's clear? So I know you have lots of questions. We can discuss it after the lecture just right now before we get out of time. I mean, I didn't want to silence everybody, but if there is no question about the formulation here, let's go forward, and probably the question going to get answered. Okay, so now that I do this, I'm going to compute this vector. This is what I'm going to call it attention vector. So this attention vector is nothing but the hidden state, but a kind of combination of all the hidden state you had over time, right? So it's somehow having a bit of hidden state in time 2, a bit of hidden state at time 5, a bit of hidden state at time 10, but how much of each of these hidden states is there is essentially the amount proportional to those weights that you have made, right? Questions? Everybody's clear? So if you got no question, then let's go for the last part. So now, if I am at the decoding part, every single time I have this state coming in, I get the new state, right? And out of that new state, I am capable of computing the queries. I'm capable of comparing the queries with the keys, right? I'm capable of computing the weights, right? And out of those weights, I'm capable of computing the attention. So I am just compressing everything inside this single box here, right? And I'm getting the attention at that particular time. Now that I have the attention, I just do decoding. So I get the attention, and I pass it maybe through one linear layer. I just activate it by a softmax. Now I have a probability. That probability is a better probability as compared to the case where I solely decide based on my hidden state. Okay? Everybody's clear what I'm doing, at least computationally here? So we're going to talk about this again next time when we do self-attention and it gets more and more clear. But any questions regarding how I did the process. So if I want to summarize it, I am essentially computing my hidden state. I am essentially computing my hidden state, and that hidden state, out of the hidden state, I'm computing attention, and out of that attention, I'm computing my output. Okay? Yes?
Value is not yet introduced in this attention mechanism.
Sorry?
Value.
Which value you mean?
Value, like key query value.
Oh, no. Value, we are going to do it in self-attention later, right? So we are still doing attention. It's not self-attention, which is in transformer. So one step left. Yeah, that is what we have next time. But you can somehow think of these values here. These H values are going to be the values later, okay? But we yet don't call it value. We call it yet hidden state, okay? Questions?
Does it always guarantee to pay attention to the right word in this condition?
I mean, it's deep learning, right? You cannot guarantee, but when you train it, it's going to do that, right? Okay. So, any other question? No question? Okay, so your output is going to be computed out of your attention and your hidden state at that particular time. And then what we can do, we can essentially compute the probability right away. This is what you do if you just want to do one layer of attention. Or you can take this attention as, again, one input to another same process. You repeat the same process with attentions being the input this time, and you keep on going upwards, right? Everybody's clear? Okay. So now, once you're doing this, you're going to see that this is going to hugely improve the accuracy of your decoder, because this is giving your decoder a kind of so many ways to put attention on the input sequence. It's not getting all the information through one bottleneck, and this is much more efficient as compared to the classical basic encoding decoding. Now, one last thing. First of all, let me just go over the whole end-to-end process once again. So if I start from the input, every single time that I'm doing encoding, I'm going to generate a key, right? And those keys are all generated once I'm over with the input sequence. Then I start doing decoding. Every single time that I do decoding, I get one query, right? Now, if I want to convert that query into some final conclusion, one final token, I have that query. I compare it to every single key. Out of that comparison, I compute one probability vector, that is my attention weight, and I use that attention weight to compute the attention vector. That attention vector is the guy who is going to compute for me the output probability, right? Everybody's clear? Okay, so that was the idea of attention, and now you can go through the whole training process as before, right? So now when you want to do the training, you're going to start with putting your input in. Now you generate the whole encoding and the keys. Then you go for decoding. You generate decoding and, the queries and decodings. And once you are all over with everything, then this is going to be the forward pass. When you are over with the forward pass, you are able to compute your loss exactly as before. Nothing is going to change, right? You compute your loss. From the loss, you can simply move backward, right? Every single time at the decoder, from the loss, you get to the attention. From the attention, you're going to get to the weights. From the weights, you're going to get to the queries and keys, right? From the queries and keys, you're going to get